So these notes cover relations and functions. So a relation is just any set of ordered pairs with an x and a y value. So I could have a set of ordered pairs that looks like this. 2, 1. So that's 1 point that's in my relation. 3, 2. And then maybe one more point, 4, 1. So this would be a relation. It's just a set of ordered pairs. It could have finitely many or infinitely many points, just any set of ordered pairs. Now, a function is a special kind of relation where each input value corresponds to exactly one output value. So this is another way that people commonly will draw a relation. So in this column, I'm going to have x values. Let's say I have 2, 3, 4, and 5. And in the other little bubble, I'm going to have y values. 4, 7, 10. And then the way you say that they match up is you draw an arrow. So 2 is going to, we say it maps to 4 because we have 2 going to 4. Let's say 3 also maps to 4. 4 goes to 7. And 5 goes to 10. So in this relation, every single x value maps to only one y value. So that's what makes it a function. Something that's not a function could have an x value with 2 separate y values. The domain is just the set of all the x coordinates. So the left bubble is the domain. And the right bubble is the range, all of the y coordinates. So there's some special kinds of functions. A one-to-one function is a function where each element of the domain pairs to only one element in the range. So you can see the difference between a one-to-one and then this other one is called an onto, where each element of the range is corresponding to an element of the domain. So notice in the first example, we have C here. C is not being used, so that means it's not onto, but it is one-to-one because all of the elements in the domain or all the elements in the range have one element corresponding in the domain. In this example, we can see that the second one is not one-to-one because C has 2 lines going in. So it's onto because all 3 of the elements in the range have an arrow going to them, but C has 2 arrows going to it, so that means it is not a one-to-one function. And then if it's both of them, then it's called both one-to-one and onto. A fancy word for this is bijective. It's the word grown-ups use when a function is both one-to-one and onto. So, given the following relation down here, we want to state whether it's a function, and then state its domain, range, and whether if it's one-to-one, onto, or both. So we can list out the domain. So we can write the domain just like this. I use a D. And then we just want to list all of the x values. So we have -6, -5. I'm just grabbing the first number in each of these ordered pairs. -6, -5, -3, -1, and 6. So that's the entire domain of this function. And then the range is all the y values. So we have, again, I'm just going to list all the second point, or the second coordinate of all those things. So we have -1, -9, -7, +7, and then it says -9 again, but we already wrote -9, so we don't need to write it again. So The way we can tell if it's a function is if any of the x values repeat. And since we have -6, -5, -3, -1, +6, it is a function. So it is a function. And then we can tell if it's one-to-one if every element in the range is only used one time. But notice, -9 repeats, right? So because -9 repeats, it is not a one-to-one function. Not 1, 2, 2. Not a one-to-one function. Not a one-to-one function. So it is a function because the x values don't repeat, but it's not one-to-one because the y values do repeat. So there's a couple of different kinds of relations we can deal with. We can have a discrete relation, which means you have a discrete relation if the domain is just a set of individual points. Or in fact, it could be like if the domain of a function were only integers. Because remember, integers are -1, -2, -3, and also the positives, but no fractions, no decimal numbers. So this would be discrete because there's always there's always space between each element in the domain. As opposed to a continuous relation where there's an infinite number of elements and you would graph it with a smooth line. So in a continuous relation, the domain could be an interval of real numbers. So I'm going to use the symbol for real numbers. So the pictures here, we have graph A is discrete because they're just separate points. And there could be infinitely many points, but because there's always some set amount of space between them, that makes it a discrete relation. As opposed to a continuous relation where we can just draw a straight line that connects all of the points. So one way to tell if it's a function based on a graph is if it passes the vertical line test. So if a vertical line intersects a graph in more than one point, then that graph is not a function. So on the left, the vertical line only intersects once, so that one is a function. But on the right, obviously, any vertical line would intersect the function twice. And you can connect this back to the definition. If the vertical line is intersecting the function twice, that means every x value, the inputs, has two outputs. Every x has two y's. Which, going back to our definition, in a function, every x can only have one y value. So, just using the vertical line test, we can see whether the following two relations represent functions. So the one on the left is a discrete relation, remember. It's discrete. It doesn't mean it moves quietly. That means there's space between the points. So it's discrete, and it is a function because no matter where I draw a vertical line, right, there's no points like stacked on top of each other. So no matter where I draw a vertical line, it'll never intersect the graph more than once. So function, it is. The one on the right is continuous because there's no space between any of the points. So it is continuous. However, it is not a function because no matter where I draw a vertical line, it intersects 1, 2, a lot more than once. So it's not a function. So a function can also be represented by an equation, and then you would find the ordered pairs of that function by substituting in values for x to find what y is. Function notation is one way to write the equation of a function. So instead of writing y in function notation, you write f of x, and it's f parentheses x, but you say it f of x. It's not f times x. It's essentially saying y is a function of x, so f of x. The reason you use function notation is a lot of the time you need to refer to different functions. So rather than just, if you have 5 different functions, you can't say that they're all y equals something, because then you're talking about the same thing. So instead, you could name your functions f and g and h and I and j. And then you can specifically refer to functions. So to evaluate a function, so f of 3, that means I'm going to substitute 3 in everywhere I see an x. And x only shows up once in this function. So f of 3 simply means I substitute 3 in for x. So instead of x squared, I have 3 squared. And I subtract 1, so that gives me 9 minus 1. So f of 3 is equal to 8. F of 2y, so 2y is not a number, but we can still evaluate f of 2y by, again, substituting in 2y everywhere I see the variable x. So instead of x squared, I have 2y squared minus 1. And notice 2y squared, another way to say that, because squared means multiply it by itself. So this is 2y times 2y, right? Minus 1. And then 2 times 2 is 4. And y times y is y squared. So we get 4y squared minus 1. And that would be f of 2y. So this concludes the brief introduction to relations and functions notes. So that's it.